So when we consider the three phases of solid, liquid and gas in a system, we also must consider the components present in the system. So what is defined by the components? Components is the least number of different substances required to describe the composition of all phases in the system. So here let's say we have ice and water. Since ice and water is the same substance, so we consider this as one component. And water and ethanol are different substances, so we consider this as two components in the system. And let's say we have water and tetrachlorocarbon. These are also considered as two components in the system. So here we have the number of phase and component. Let's take a look at air here. We have oxygen, carbon dioxide, and nitrogen gas. So all of the gases are in the same phase, which is gas phase, but the component having many here. Let's say we have ice, water, and vapor. This is the same substance, so we have one component, but we have three phases. Let's say we have sulfur alpha and sulfur beta. This system having same substance, because the difference is only on the type of the sulfur. We put here as one component, but having two phases. Okay, now let's take a look at the degree of freedom, symbolized as F. So what does it mean by degree of freedom, or also called as variance? This degree of freedom is defined as the number of intensive variables that can be independently varied without changing the phases of a system. The variable example here, we have temperature, we have pressure, and also the composition of the components in a system. So in this case, we are using the phase rule, which is the general relation among the variance F and the number of components C and the number of phases P happen at equilibrium for a system of any composition. So how to calculate the degree of freedom here? We have the formula F equal to C minus P plus 2. So F is referred to the degree of freedom, the number of variables that can be changed independently without changing the phase of a system. And P is the number of phases. Phases are mechanically separable constituent, and C is the number of components, which the chemical constituents that must be specified in order to define all phases. And 2 is referred to the two intensive parameters, which are temperature and pressure, and all of this only applies to a system in a chemical equilibrium. For one component phase equilibrium, for example, here we have pure water, we can calculate the degree of freedom for this pure water by having this formula where F equal to 1 minus P plus 2, 1 referring to the one component of the pure water, and 1 plus 2 equal to 3, so F equal to 3 minus P, and C here is the component of water. And in this case, we have to consider that the degree of freedom must be equal or greater than 0, and the phase must be equal or greater than 1, and the value of P must be within 3 to 1. So how about we replace the value of P here with 1, 2, and 3. Let's say the phase equal to 1, so the degree of freedom is equal to 2. So this system, we call it as a bivariant system. In this case, the system depends only on two parameters. It is either temperature, pressure, or the composition of the system. And how about P equal to 2, the degree of freedom equal to 1. So this is what we call as univariant or monovariant. The system only depends on one intensive variable only. It's either temperature, pressure, or composition. And here we have P equal to 3, so the degree of freedom equal to 0. So this system, we call it as invariant system. In this case, the system does not depend on the three intensive variables. Taking water phase diagram as an example to calculate the degree of freedom, where we have the formula here, F equal to 1 minus P plus 2. So each point in the water phase diagram, we can determine the degree of freedom. Let's say here we have a region where the solid liquid gas exists as one phase, as the supercritical fluid. So we substitute the value of 1 inside the P, so we can get the degree of freedom at this region is equal to 2. And then at line OA, AD and AC here, OA, AD and AC, each of the curve represent two phases in equilibrium. So we substitute 2 inside the P value here, so we can get F equal to 1, the degree of freedom equal to 1. At point A here, where we have the system coexists all together, solid, liquid and gas, so we have 3 phases, so we need to substitute 3, the value of 3 inside the formula, so we can get the degree of freedom equal to 0. Vapor pressure. In this case, a solvent in a closed container reaches a state of dynamic equilibrium. Okay, so the pressure exerted by the vapor in the headspace is referred to as a vapor pressure of the solvent. A substance or the solvent with a high vapor pressure at normal temperatures is often referred to as volatile compound. So here we have an open system and a closed system. In open system, the evaporation of solvent is happened, so there is no dynamic equilibrium in the system. But here, when we have the closed system, we have the dynamic equilibrium. The liquid will turn into vapor and the vapor will turn into liquid back. So when the evaporation has reached the equilibrium with the liquid surface is said to be saturated. So here we can see that the liquid is volatile in this system, so it can exert the vapor pressure. There are several factors that can affect the vapor pressure. The first one is the type of molecules that make up a solid or liquid in determination of its vapor pressure. If the intermolecular forces between molecules are strong, meaning that we will have low vapor pressure. If the intermolecular forces are weak, so we will have high vapor pressure, meaning that the molecule is volatile. At high temperature, more molecules will have sufficient energy to escape from solid or liquid, meaning that the molecule will absorb the heat in the form of energy for the bond breaking. At low temperature, fewer molecules will have sufficient energy to escape from liquid or solid. What is Raoult's law? Raoult's law describes the relationship between vapor pressure of solvents and its mole fraction. In this case, the vapor pressure of the solute containing the solution Pa is equal to mole fraction of solvent Xa times or multiply the vapor pressure of pure solvent P0 A. So we have this formula for Raoult's law, Pa equal to Xa times P0 A. In this case, only the solvent A contributes to the vapor pressure of the solution. And then we also need to calculate the mole fraction, X. Mole fraction of component is the number of mole of a component divided by total numbers of mole of components. Let's say we have two components A and B, so we want to find the mole fraction for component A. So we have here Xa equal to number of moles for component A, symbolized as Na, and the total number of moles of the components in the system, Nt. So to calculate Nt, we have to add Na and Nb. This is the sum of the number of moles. So this is how we want to find the mole fraction for component A. And if we want to find the mole fraction for component B, we are using the same formula. Vapor pressure lowering, meaning that we want to reduce the current vapor pressure exerted by a pure solvent. Let's say here we have a system of pure solvent in a closed system. The solvent evaporates. So we have here a very high vapor pressure. And then here we have a solvent which already added with a solute, the yellow one. So there will be less vapor pressure exerted by this system. Okay, so the presence of non-volatile solute means that the fewer solvent particles at the solution surface. So here the solvent molecule is fewer than the pure solvent. So there will be less solvent evaporates in the system. Since the addition of a solute to a pure solvent will have to reduce its vapor pressure, so from this information we can relate it to a phase diagram. So here we have the black curve which represents the melting or freezing point. Here we have another black curve here which represents the boiling or condensation point. So when the addition of solute, we can see the changes from the freezing point where the temperature is reduced to a certain value, and the boiling point, the temperature is increased to a certain value. So we have the new temperature for the boiling point of the solution, and this one is the original boiling point of a solvent without the solute. And the freezing point, this one is the original freezing point of a solvent, and after addition of solute we have the new freezing point of the solution. So from this phase diagram we can see that the addition of a solute is affecting the changes in the temperature for the freezing and boiling points. Due to the changes happen when we add a solute to a pure solvent, so causing a vapor pressure lowering, so we need to calculate the vapor pressure using the Raoult's law here. Okay, the PA naught is the vapor pressure of pure solvent and XA is the mole fraction of the solvent. Since the addition of a solute, we have to consider that another mole fraction for a solute where we have XA plus XB equal to 1, and XB is the mole fraction of a solute. So we rearrange back this equation into this one, so we can get the XA equal to 1 minus XB. After that we can substitute this formula into this Raoult's law, so we can get the new formula here, PA equal to 1 minus XB times P naught A. And then we expand the equation and we can get here the final equation for vapor pressure lowering is the change of P equal to XB times P naught A.